So normally what we do is I'll do half the notes in one video and half the notes in the second video, and we kind of split it up over 2 days. However, this is a rather short set of notes, so we're going to complete this in one video. It's also going to help us stay caught up given the number of days that we've been missing here lately, and make sure that we stay on track. So we're talking about library of functions, and this is really kind of a basic set of notes, a small little lecture that we want to go through, because as we go through this course, and if you go through any other math courses beyond the college algebra class, there's going to be a handful of functions that you just kind of want to intuitively know immediately what they might look like, and you can get a mental picture. One of the first ones that always comes to mind is the graph of x squared. I believe everybody knows that's a parabola. The vertex is at the origin, it opens up, symmetric about the y-axis. That's one of the first ones that comes to mind. But there's going to be several others that we're going to encounter throughout the remainder of this class, and then, like I said, in subsequent classes beyond this, where it's just a good idea to make sure that you have just this mental idea or mental picture of what some of these functions look like and how they behave. So we're just going to start right here with the first one. It's the square root of x. The square root of x is this half parabola that's kind of laid. It's the parabola x squared rotated 90 degrees, and then we just look at the upper half of that. Because if we were to consider this lower half right here, what that would imply is that we have positive x values that we can take the square root of that would somehow generate negative y values. And since we know that is not possible, we only have this one half of the parabola that you see here on the left side of the screen. The the domain. Okay, remember that's the x values. This function is defined from 0 to positive infinity. And it has an x-intercept at the origin of 0, 0. It's neither even nor odd because there is no other component of this graph where we can express any kind of symmetry to it. And it's increasing on the interval from 0 to positive infinity. It's continuing to rise. And it has an absolute minimum at 0. We talked about absolute max, absolute mins, local max, local mins in the last set of notes. What we want to do is we want to take that graph and we want to kind of build on it and determine what we can figure out about the graph of the cube root of x. So part A asks us to determine whether the cube root of x is even, odd, or neither, and then just state whether or not the graph is symmetric with respect to the y-axis or with respect to the origin. So remember, to determine if a function is even, odd, or neither, you evaluate it at the opposite of x, so negative x in this case, and we're taking the cube root of negative x. So how does the cube root of negative x compare to our original function? The cube root of negative x is actually the complete opposite of the cube root of x. So recall that whenever we evaluate this, if we get the complete opposite function, then what we have is an odd function, and that symmetry for an odd function is origin symmetry. So this is symmetric with respect to the origin. All right, part B, determine any intercepts that the graph may have. So to find the x-intercept, you set y equal to 0. So let's just set the whole equation equal to 0 and solve for x. I have to cube both sides of the equation to get rid of the cube root. 0 cubed is still 0, so we have an intercept at the origin. And then the y-intercept, I think probably is already obvious to you, but we'll check anyway, is when x is equal to 0. Well, the cube root of 0 is 0. So again, we have origin, and that's the only intercept that we have for this particular graph. Part C wants us to graph the function, and we can do a table of values and do some test points. but this was one, it may be easier just to do it on the calculator and look at what the graph looks like. But just to give you an idea, let's say we have some x values here. We'll say -8, I don't know, -1, 0, 1, and +8. Those were not by accident, they're perfect cubes. So the cube root of -8 is -2. The cube root of -1 is -1, 0, 1, and 2. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. So at -8, our value is -2. At -1, our value is -1. At 1, it is going to be 1. And then at +8, 2, 4, 6, 8, it's 2. So we get this graph right here. And if you recall anything about any of our other graphs that we've looked at previously, this is essentially the graph of x cubed, which I'm drawing here in green. And it's kind of rotated and flipped. So x squared kind of looks like is a parabola. Square root of x is a parabola laid on its side. Cube root of x, same thing. It is the graph of x cubed, rotated and flipped. So that's what we get when we look at the cube root of x. I will show you on the calculator the very same function. So let's do the cube root of x. There you go. Hey, that looks just like what we drew. So that is the cube root of x. That's one of those functions that you just kind of want to, again, have a mental picture of what it's going to look like. Some properties of the cube root of x. Domain and range is the set of all real numbers. So we can put in any x value and generate a new y value. The x-intercept is the origin. The y-intercept is the origin. It is symmetric with respect to the origin, so the function is odd. We verified that algebraically. And this function is constantly increasing from -infinity to +infinity. And it has no local max or local min because it's continually increasing from left to right. It never has any kind of minimum value. It never has any absolute, or it never has any maximum value. Sorry, I don't know why I'm choked up. Example 2 is the absolute value function. Absolute value, again, one of those that really you may have already seen several times over, so you probably already know what it looks like. But we're going to go through the exercise again anyway, just to be sure. So for part A, we want to determine whether it's even, odd, or neither. So that is where we evaluate the function at the opposite of x. The absolute value of -x is the absolute value of x. So that is the exact same function that we started with. So if it is the same function, then remember that means it is even, and it has y-axis symmetry. Determine the intercepts, if any. So we do the same exercise that we did on example 1. We're going to set y equal to 0. And the only thing that we can take the absolute value of to get 0 is 0. So x has to be 0. So there's the intercept. The other alternative is, what is y when x is 0? Well, that's also 0, so we only have the origin as our only intercept. And then part C, we want to graph the function. So let's come up with some x values and their corresponding y values. So let's just do -4, -3, -2. That's enough. When we take the absolute value of all these, the absolute value of -4 is 4. -3 is 3, -2 is 2, and so on. So we can plot these points. So at -4, 2, 3, 4, we have a y value of 4. At -3, we have a y value of 3. I think you kind of get an idea what this graph is going to look like. The absolute value function is, it's a v. All right, absolute value function is going to be a v because all of our values should come back positive, so everything should be pretty straightforward as far as that graph goes. We can again verify this graphically on our calculator. Delete that. I wonder if I can do it this way. No. All right. Excuse me. There's the absolute value. It's the V. Excuse me. So some basic properties of the absolute value function. Domain, again, is the set of all real numbers. The range is all y such that y is greater than or equal to 0. Forgot my curly braces there. The x-intercept is at the origin along with the y-intercept. It's symmetric with respect to the y-axis, so that makes it an even function. It is decreasing on the interval from negative infinity to 0. And then once we get to 0, the graph begins to increase from 0 to positive infinity. It only has an absolute maximum, or absolute minimum at 0, and that is when x is equal to 0. These next few functions that we're going to look at, I'm not going to go into a whole lot of detail with them because these are ones that you should know very, very well because you've probably seen them ever since you first started learning about all this math that has letters in it. A constant function is just a horizontal line. That's when y equals some constant number. That's what we see right here. This notation, this funny looking E, means element of. And then this special looking R is just the real numbers. Okay, so what that says with mathematical notation is that B is an element of the real number. So B can be any number. It's always just going to be a horizontal line whenever we plot its graph. The identity function, y equals x, essentially. That is the 45-degree angle line that passes through the origin. When x is 1, y is 1. When x is 2, y is 2, and so on. The domain of the identity function is all real numbers. It has a slope of 1. Let's see, I forgot to mention too, the domain of the constant function is all real numbers. And its range, though, is whatever that y-intercept is. That's all the range is for that particular function. The square function, x squared. Parabola opens up, vertex at the origin. Domain is a set of all real numbers. Its range is whatever the vertex is, up to positive infinity. Unless this graph is flipped, then its range is from the vertex down to negative infinity. It's decreasing from negative infinity to the vertex, so in this case negative infinity to 0, and it's increasing from 0 to positive infinity. Cube function, we made reference to the cube function at the beginning of the notes when we looked at the cube root. Cube function has a domain of all real numbers. It has a range of all real numbers. It only has one intercept, and that's at the origin. Now keep in mind when I talk about these intercepts and the domains and the ranges, it is always predicated on the simple fact that we're looking at these base functions. We're not talking about any transformations with any of these functions. And this function is constantly increasing from negative infinity to positive infinity. The reciprocal function. We get this hyperbola with the reciprocal function 1 over x. It has a vertical asymptote at x equals 0. So its domain is the set of all non-zero real numbers, or you can just say negative infinity to 0 and 0 to infinity. It has no intercepts. The graph approaches the x-axis, it approaches the y-axis, but never crosses either. And it is symmetric with respect to the origin, so it is an odd function. You can verify that algebraically if we evaluated this function at the opposite of x. That is the complete opposite of the original function we started with, therefore proving that it is odd. The next one is an interesting function that some of you may or may not have seen. I venture to guess the majority of you have not seen this function. It has two different names. One's called the greatest integer function. Two, it's also called the floor function. So the greatest integer function, or the floor function, just takes some given value and if it's 2.9, typically we round up, right? Well, the floor function, you just round it straight down to the closest integer. So 2.9 would round down to 2. 2.3, 2. 2.7, 2. Doesn't matter. When you get to 3.1, now we drop down to 3. So that's where we get this stair-step graph. So any value from 0, defined at 0, up to but not including 1, is going to give us this little horizontal line from 0 to 1. And then we have that open circle at 1 where the function is not defined on this particular line, but then it jumps. And this is called a jump discontinuity. The graph jumps from at 1 up to where it is defined at 1. When x is 1, y is 1. And it's defined to be 1 all the way up until we get to 2, and it jumps again. It's defined at 2 until we get to 3, and then it jumps again. So this graph is not a function because it cannot be, it is discontinuous and it cannot be drawn without picking our pencil up off the paper. That's one of the primary components of a graphical representation of a function. If you can't draw it without picking up your pencil, it's not a function. Piecewise functions. These are, sometimes they're a little bit more of a challenge than they really should be. If you're just very careful with how you do these, then they're actually relatively simple to work with. We want to just go ahead and do an example. We're here with number 3. We want to graph the function. We actually want to do several different things. The first thing we want to do is find f of -2 there in part A. So that just means we evaluate the function when x is equal to -2. So if we look here on our intervals given in the function, when x is -2, it falls in this first interval. So that means we evaluate the function using this piece of the function. So at -2, we put -2 in for x, and we evaluate, and we're going to get 5. So at -2, this function evaluates to 5. The second part says evaluate the function at 1. So when we look, when x is equal to 1, this function is constant. It's equal to 2. So when x is 1, the function is equal to 2. And the last component is find the function when when x is equal to +2. So this third definition for the piecewise defined function says that when x is greater than 1, we evaluate x squared. So for x is equal to 2, we just have 2 squared, and that function is equal to 4. So let's determine the domain of the function by looking at what we know. This function is only defined from -3. It is defined at +1, because here it's not defined at +1 on this interval. It's from -3 up to, but not including 1. Then we jump here to 1, and it's defined again. And then it's defined for everything greater than 1. So the domain, and we'll see that here in a second with the graph, the domain is -3 to infinity. Any number in there, in that interval, we can choose, and that function will be defined. If we chose -6, the function is not defined. Says for part C, locating the intercepts. That may be easier to do if we just look at when x is 0. The only interval where x can be 0 is this first one, because 0 falls in the range of -3 to 1. So we evaluate -2 times 0, and we're going to get our y-intercept would be +1. So at 0, we have a y-intercept of +1. And we need to determine if we have any x-intercepts. That's going to come when we look at the graph itself. So let's take a look at the graph here with part D, and we'll come back to part C. Part D says to graph the function of f. So we're going to graph all three. Let me erase all this mess, because I'm going to color code the graph. That'll make it easier to understand. Let's graph the first part of this using this pink color. So it's the graph negative 2x plus 1. So we have a y-intercept of positive 1 and a slope of negative 2. So that's going to give me this line right here. Graphing the line is the easy part, but now we need to look at the restrictions. This function is defined from negative 3. So negative 3, the graph, we don't see that part of the graph, but we know that it extends up to here. So there's negative 3. We'll put a closed circle because it is defined at negative 3. And then at positive 1, that erased my whole line, we're going to have an open circle. So there's our graph, negative 2x plus 1 defined on negative 3 to positive 1. Now we want to graph our second part. I'm going to use green, and that's where f of x equals 2 when x is equal to 1. So it's just going to be a dot. That's it. And then the last part is going to be in orange. It's the graph of x squared for x greater than 1. So remember, the graph of x squared is going to look like this terrible function here. I did a bad job with that. But anyway, you get the idea. That's the parabola of x squared. But it's only defined where x is greater than 1. So at 1, we're going to have this open circle. And then that is the continuation of the parabola. So that's how you graph a piecewise function. So that was part D. So when we come back to part C, we did find we have this x-intercept or this y-intercept, and we only have one x-intercept, and that is on the first graph. So to find the x-intercept, we set y equal to 0, and we solve for x. So subtract 1, divide by negative 2, and we get an x-intercept of 1/2. And that seems to correspond with what we drew. If this is difficult to try to keep up with or to follow along, don't panic. We will talk about these more in class. But this is just to get you an idea. I think if you just stop, look at it for a minute, I think you can probably really see how all this comes together. If not, ask questions. Not a big deal. Part E, use the graph to find the range of f. So where is it defined? Vertically. So the lower bound is right here at -1, but it's not defined to be -1. But then it is defined all the way up. The parabola continues on infinitely. So it is defined all the way up to positive infinity. So our range is all y such that y is greater than, but not greater than or equal to, -1. And it goes on up to infinity. So we can just stop right there. There's our range. And then the last part is f continuous on its domain? Now that's not, is it continuous on all x values? It's asking only, is it continuous on its domain? So starting in its domain values, we start over here at -3, where it is defined. And if I imagine drawing vertical lines up from every point that I'm drawing off of this line horizontally, will it intersect part of the graph? The only real question we have is right here. Fortunately, it is defined to be 2 at this point, even though we have these two open intervals for the other two graphs. So yes, this graph does end up being defined on its entire domain. We can just say yes, it is defined across its domain. All right, and that is the piecewise defined function. I believe, yeah, that's the end there. So that's it for this set of notes. I hope that you don't have too many questions, because we could certainly spend our time moving forward. But again, if this is something you're stuck on, then I don't care to stop. We'll talk about it. We can get caught up other ways. I really would. There's not that many problems on here as far as the homework goes. So I really would like to maybe take a look at these 8 problems in class together on Tuesday. So please, please, please try to work through some of them. Make your best effort. Get frustrated. Frustration is good. It helps you understand where you're making the mistakes. But I want you guys, most importantly, to think about what you're doing. So I hope everybody is ready to be back at school. Hopefully, with all the rain in the forecast, we might not have to miss any more days, but who knows. So I'm rambling. That's it. You guys have a great night, great afternoon. You guys will be watching this hopefully in the library on Monday. But I will be happy to answer any questions you have. Take care.